Hello and welcome to another one of D's ADD videos. We're going to be looking at a linear transformation example. In this case we're going to look at an R2 to R2 transformation. So this would be your U, big U space, this would be your big V, this is your domain, this is your codomain. And the transformation we're going to look at is take every x value plus every y value for the new x value, which is right there, and then every y value becomes the 2x. Alright? So what do? What is the first step? Well, we pick vectors randomly, x1 and y1, x2 and y2, both in vector space U, or the domain. And we need to ask the question, is it preserved under addition? If I do the transformation of each one added together, will it still equal the individual transformations added? So in that case, what you do is you plug in your x1 and x2 and y1 plus y2 into the transformations, see if you can get the individual transformations out of the ones that were plugged in unified. So what do I mean by that? Well, here's the first step. This first step is just the vector addition here. Is technically the first step, actually. But then by the definition of our transformation that we have here, our transformation said what? Take every x value and add it to every y value. So if you do that, you get x1 plus x2 plus y1 plus y2. And then the y value was twice the x value that we had here for our transformation. Right? So what we're doing is we're evaluating this expression right here. Then at that point, what we can do is we can use the power of distribution to distribute that 2 through. And then by vector addition in reverse, what we can do is we can go from this step and this step. That's addition. Alright? And when we do that, we end up with this. And as you can see, these two vectors are indeed the individual transformations we were looking for. This one here is the transformation of x1 comma y1 plus this one here, which is the transformation of x2 comma y2. So we're good to go there. So what we can say now is it's preserved under vector addition. And then here we have the scalar multiplication. So let C be some scalar, all scalar values actually. And if we plug in a C times the variable everywhere, can we get it to be C times individual transformation? So here we have C times a variable plugged in. If you factor out the C, sure enough you get the scalar constant times the actual transformation. So now we can say that the transformation preserves scalar multiplication. And because both were preserved under the transformation, you can say yes, it is a linear, therefore linear transformation. Okay. This is a specific type of linear transformation. This is called the linear operator. Sorry, can't speak. It's a linear operator because it's a transformation of a vector space onto itself. So a linear operator. I don't think you guys will really need to know that, but anytime you get a transformation onto itself, then it's an example of a linear operator. Alright, so that's for vectors. Make sure you check out the example that doesn't work, that's not a linear transformation. Also look at the matrix transformations. Alright, so I hope I have cleared up any confusion that you might have. Again, make sure you check out the examples, and most importantly, practice, practice, practice. Thank you, and have a nice day.